Hi scholars, Ms. Beglin here with your Unit 2 Molecular Structure, Topic 1 Molecules, Lesson 6 Molecular Geometry or Shapes, independent work. So we have been talking extensively about Lewis structures and hybridization, and the really cool thing about these concepts is that they hint at the shape that molecules take in three-dimensional space. And that's exactly what we're going to be talking about in this video, the shapes that molecules take in three-dimensional space. There are two ways we describe the shapes of molecules. First is we have some standard designations for what the shapes look like. And we can refer to this table to determine the shape. So in this column, we can look at the number of electron domains around an atom. And then as we move this way, our number of lone pairs increases. And it tells us what the shape is called. So if we have 2 electron domains and no lone pairs, that shape is linear. If we have 3 electron domains and no lone pairs, the shape is trigonal planar. If we have 3 electron domains and 1 lone pair, the shape is bent or angular. So we're really just describing the position of molecules around each other using these standard words. Normally, you would have to memorize this. Your tests will be open notes. The AP exam might be open note as well. So what I recommend you do is copy this into your note. Let's look at some examples. Okay, boron trihydride. I have 3 electron domains and 0 lone pairs. 3 electron domains, 0 lone pairs. My geometry is trigonal planar. Methane. I have 4 electron domains and 0 lone pairs. My shape is tetrahedral. Ammonia. I have 4 electron domains and 1 lone pair. Trigonal pyramid. And water, I have 4 electron domains and 2 lone pairs. Bent or angular. I prefer bent. Okay. The second way we describe the shapes of molecules is using bond angles. This is basically a measure of the angle between bonds that are right next to each other. So when we have sp hybrid orbitals, they have a bond angle of 180 degrees, which you can see here. When we have sp2 hybrid orbitals, the shape is generally going to be trigonal planar, and they have a bond angle of 120 degrees, which you can see here. Now, tetrahedral is where things get a little weird because our Lewis structure for a tetrahedral molecule would imply that the bond angles are 90 degrees. But remember, molecules exist in 3-dimensional space. So we have our carbon with a hydrogen on top, 1 to the side, and then 1 moves forward and 1 is backwards. So we have a tetrahedral shape and a bond angle of about 109.5 degrees. So now that you know what bond angles are, you can record the bond angles that are listed in this table in your notes as well. Why do these geometries exist? Why does this happen? It all goes back to Coulomb's law. Electrons repel each other. And so we say that molecules automatically adopt 3D shapes to minimize the repulsion between electron pairs and maximize the distance between them. We call this valence shell electron pair repulsion theory because we're talking about the repulsion between electron pairs in the valence shell, or VSEPR theory. So you'll commonly see these geometric designations referred to as VSEPR geometries. I want to draw your attention to the bond angles of our molecules with 3 and 4 electron domains. You'll notice that as you increase the number of lone pairs, the bond angle decreases. This is because while lone pairs are localized, they are slightly more delocalized than bonding pairs, which are super localized between 2 atoms. So this bonding pair is going to stay right there. This lone pair can move around a little bit because it's not crammed between 2 atoms. As a result, the lone pair will push our bonded pair slightly closer. So in terms of what you need to know, the angle for a tetrahedral geometry is 109.5 degrees. Trigonal planar is 107.5 degrees. And a bent or angular geometry is 104.5 degrees. And you should know why that is the case, because of the increased repulsion of lone pairs. A quick reminder that geometry is based on electron domains. So ozone, our central oxygen, has 3 electron domains. We treat this double bond as though it were just 1 bond. So our shape is bent. In our nitrate anion, nitrogen has 3 electron domains, 0 lone pairs. This had 1 lone pair, which is why it's bent. 0 lone pairs. So its geometry will be trigonal planar. And this is why resonance structures are preferred to hybrid structures, because it's really easy to determine, when looking at a resonance structure, it's really easy to determine the number of electron domains, which makes it really easy to determine the hybridization and the molecular geometry. That's all, folks.